Friends, this is Sarita Agarwal. And today I'll discuss relations, right? Relation is one of the useful important topic in mathematics, right? So for that, I need the screen sharing space. So relations. Okay. Relation is a word derived from English, which means that the two objects are related if they have recognizable connection or link, right? So what is the purpose, what is the use in mathematics? In normal English means if in a class we have the class with boys and girls, so we have boys and girls, right? So class is a set in which we have boys and girls. If we take A as a set of boys, B consisting of girls, then the relation here, relation set according to mathematics, is A and B chosen from the class such that A is a brother of B. A is a brother of B. A is a brother of B. Or we can establish another relation. Instead of this, we can establish another relation. That is A, B, again chosen from the class, such that A is a sister of B. These are the human relations, right? What is the mathematical relations? We studied natural numbers, right? In natural numbers, we have three types of relations. Consider the set of natural numbers. We have three relations. That is, three relations. And these three relations are less than, equality, and greater than. Means if A and B are in natural numbers, then either A is smaller than B. This is one of the relation. A can be equal to B is another relation. A can be greater than B. That's a mathematical relation in natural number. Similarly, if we see another relation, right? So that means we can draw that B equal to 4A. That's another relation. How to write this relation? We can write the relation as this A and B are chosen from this set of naturals, right? And such that A is less than B. Similarly, we can write for equality. Similarly, we can write for greater than, right? And for the another relation, Means I can write A and B chosen from the set of naturals such that B equal to 4A, right? Similarly, if we take the set of reals, we can write another relation is A and B are chosen from reals such that B equal to A by 2. It's a relation, right? These are the relations. Since we have taken this relation, so how to write mathematically? Mathematically. So, how to write relation in mathematically? Mathematically. If A is related to B, then we write or. So that means this is, we can take this as one relation, this as another relation, and this as another relation. This is another relation. So these are the relations. Mathematically, we have this. Now, since we have taken this R as a set, we know that we have empty set, and this R itself is a universal set. So, what are the relations for this? Right? We are coming to that. We take A, the set consisting the numbers just 1, 2, 3. Right? These are the three numbers. And then we take a relation, that is A and B are chosen from A such that the difference between them is 10. Then you can see that this is what? We take either A 1, 3 or we take B as 1, 2, 3, but in any case, we are not getting A minus B equal to 10. And that means this relation is empty. Right? So this relation is empty. Right? What is a universal set? It's a universal. This, we know that this R is this relation set. When we are taking this A and B from this A cross A, means the Cartesian product, right? So it is what? It is this, we have this 1, 1, we have this 1, 2, 1, 3. Then similarly we have 2, 1, 2, 2, 2, 3. Then we have this 3, 1, 3, 2, 3, 3. So this set is this Cartesian product, right? So this is this set is the, when the relation is the Cartesian product, is the order pair of naturals, order pair of A's, right? Then this set is called the universal set. Means this gives us that this relation is always a subset of this Cartesian product. This is always a subset. If we are taking naturals, then this relation is a subset of n cross n. If we are taking reals, this is the subset of this r cross r, right? That is the reals, right? So this is what is here. So this R is a universal set if it is equal to the ordered pair of a given set or the Cartesian product of the set. Cartesian product of the set. Of the set, right? So this is what is there. We can write this as this. I am representing this reals with the Greek symbol of R. So when this R is this empty set, means when the relation is empty, we call this empty relation. When the relation is the Cartesian product of the set, then this is known as universal relation. Right? Now we are coming to the types of relation. Types of relations. Mathematically, we have three types of relation. One is reflexive, another is symmetric, and another is transitive. What is reflexive? What is reflexive? Reflexive is if A and B, for that firstly we define a proper way, let R be a relation on a set A. Then the reflexive is if A and A belongs to R, whenever A is in A, right? Then we say that R is reflexive. Then in this case, we say R is reflexive. Right? Reflexive. Second is symmetric. Symmetric. If AB belongs to R, then BA belongs to R for all A and B belonging to A. In this situation, we say that the R is symmetric. Transitive. If AB belongs to R and BC belongs to R, then AC belongs to R for all A, B, C belonging to A. Then we say R is transitive. right? Let me say the R is transitive. A relation R in a set A is said to be equivalence relation. Is said to be equivalence relation. Is said to be equivalence relation if R is reflexive, symmetric, and transitive. Right? Now we are coming to the examples. We are coming to the examples. Right? We can see the set, let A be the set consisting the numbers this 1, 2 and 3 only. And the relation on A is just 1, 1, 2, 2, 3, 3. Then this is the example of reflexive. Then we say the R is reflexive, but R is neither symmetric nor transitive. But R is not, this is a reflexive only, means R is reflexive, but it is not symmetric and it is not transitive. And the symmetric, not transitive. Right? Now, if we see another relation, if we have this RS 1, 2, 2, 1, 1, 3, 3, 1, and 2, 3, right? And 3, 2. Right? If we have this, then this R is symmetric, but non-reflexive and non-transitive. Non-transitive. Right? If we have this relation, right? If we have this relation, then you can see this relation is what? We have this 1, 2, 2, 3. That means 1, 3 is here. When we have this 2, 3, 2, 3, 1, 3 will not work, right? 1, 2, 1, 2, 3, 3, 2. Then we have this 2, 2. We have this 1, 3, 3, 2. Then this 1, 2 is here, right? When we have this 3, 2, 2, 2, then 3, 2 is here, right? When we have this 3, 2, 2, 3, so that means 3, 3 should be here, right? Another thing, then we have this 1, 3, 3, 3, 1, 3 is here, right? So this relation is what? Is transitive. But it is neither reflexive because 1, 1 is not here. It must be true for all. And it is not symmetric because 2, 1 is not here, right? Similarly, 3, 1 is not here, right? So you can see there, this we have 1, 2, 2, 2, 1, 2 is there. We have 1, 2, 2, 3, 1, 3 is here. We have, these are the possibilities with 1, 2, right? Now when we have 2, 3, when we have 2, 3, then it is 2, 3, 2. That means 2, 2 is here, right? And 2, 3, 3, 3, 2, 3 is here. So it works here. Now for 1, 3, we have this 1, 3, 3, 2, 1, 2 is here. 1, 3, 3, 3, so 1, 3 is here, right? Then we have 3, 2, 3, 2, 2, 3, 3, 3 is here. Then nothing is possible. 2, 2, 2, 2, 2, 3. That means 2, 3 is here. 2, 2, 2, 3, 2, 3 is here, right? 2, 3, 3, 2, 2, 2 is here, right? Then we have 3, 3. 3, 3, 3, 2. 3, 2 is here, right? And another possibility is 3, 2, 2, 2, 3, 2 is here, right? Anything, nothing else, right? So it is what? You can see here, right? This R is symmetric but non-reflexive, non-transitive. So it is transitive but it is not symmetric and non-reflexive. But non-symmetric and non-reflexive. Non-reflexive, right? Now we are coming to the another example. These are the easy examples to create and to understand the subject better. Now we are coming to the another examples. That is of the equivalence relations, non-equivalence relations, something like this, right? So we see what is here. That is, let T be the set of all triangles, right? All triangles in the plane R, in the plane with the relation in the plane with R, a relation in T is given by this R is T1, T2 such that T1 is congruent to T2. T1 is congruent to T2, right? This is the relation. We know that each triangle is congruent to itself. Since each triangle is congruent to itself, is congruent to itself means that T1 is congruent to T1 for all T1 belonging to T. That means T1 belongs to R for all T1 belonging to T, and this means that this relation is reflexive. Right? Second is, let T1 be congruent to T2. Then the congruency implies that, then that means that T2, then clearly T2 is congruent to T1. And better to write, let T1 and T2 belongs to R. That means T1 is congruent to T2. And congruency implies that this T2 is congruent to T1. And T1 and T2 belonging to this R or T are arbitrary. That means that this T2, T1 belongs to R. But T1 and T2 belonging to T are arbitrary. This means that T1, T2 belongs to R. Thus, instead of this, we can write thus T1, T2 belongs to R implies T2, T1 belongs to R for all T1 and T2 belonging to T. And this gives us that this R is symmetric, means the relation is symmetric. Third is, let T1, T2 and T2, T3 belongs to R. Right? Means T1 is congruent to T2 and T2 is congruent to T3 and this gives us that T1 is congruent to T3. But T1, T2, T3, because relation is a subset of the Cartesian product of T's, that means the T1, T2, T3 belonging to T are arbitrary. Implies it, thus we can say, therefore, T1, T2 and T2, T3 belonging to R implies that T1, T3 belongs to R for all T1, T2, T3 belonging to T. This gives us this relation is transitive. Since the relation is reflexive, symmetric, and transitive, that means the relation is an equivalence relation. So I can number that where we have this symmetric, where we have this reflexive. So here I can number this as 1, And the symmetric is where the symmetric is written.